All right, quick review from last week. Okay, remember that if we are naming an ionic compound, we write the name of the metal first, the name of the nonmetal second, change the ending to "ide" on the nonmetal. If the metal has more than one possible charge, then we figure out what Roman numeral should represent that charge, okay? And we put it in the name. And if we have a polyatomic ion, then we just simply write the name as it appears on the table of polyatomic ions. For molecular compounds, we write the name of the first nonmetal unaltered. We write the name of the second nonmetal, okay, ending in "ide," and we put in the appropriate prefixes into the name. If we're writing the formulas for ionic compounds, okay, we write the formula or the symbol for the metal and its charge above. Same for the nonmetal, write its symbol and its charge above, then drop and swap to get the appropriate numbers. And if possible, if you had like a 3 and a 6, you would simplify down to 1 and 2. Okay, so I'll put a couple up here on the board just to quickly review what we did last week. Then we're going to work a little bit on just some practice today. And then about second half of class, we'll start talking about lab reports, because tomorrow we're going to do the pre-lab stuff for our first lab, and Thursday will be our first lab. Okay, let's try this one. Okay, so for these ones, I would like you to write the names, please. Okay, I'll give you a couple of minutes on those. Okay, first one, ionic or molecular? Ionic, metal, right? Sodium is a metal, so this is definitely ionic. So I follow the ionic naming rules. I write the name of the metal, and then I write the name of the nonmetal, and I end in "ide." Sodium oxide, that's all I need. Okay, no prefixes because it's ionic. All right, second one, ionic or molecular? It's molecular. They're both nonmetals. All right, so I write the first nonmetal, name unaltered, and I write the second nonmetal. Okay, I don't need a prefix on, oh, sorry, I do need a prefix on that. Okay, disulfur. And then tri for 3, and I change the ending of chlorine to chloride. Okay, that doesn't look at all like a D and an E. Let's try that again. That's a little better. Okay, for the third one, ionic or molecular?
Ionic.
It's ionic. Iron is a metal. Okay, so I'm just going to write the name of the metal. I'm going to write the name of the nonmetal. Do I need anything else in that name? I need a Roman numeral in that name. Okay, just as a quick review, how do I know I need a Roman numeral? I go over to the periodic table and I see that iron has more than one possible charge. Okay? If the metal you're looking at looks like any of these boxes along here with more than one number there, then it's going to need a Roman numeral. So, quick review, how do we figure that out? Well, we look at the nonmetal, because nonmetals only have one possible charge. Sulfur's always a -2. There are how many sulfurs here? 3. So every sulfur has a charge of -2. That gives us a total of 6 negative charges. Ionic compounds have to balance out and have an overall charge of 0. So I know I have to get 6 positive charges from the 2 iron atoms that I have. That means every one of those iron atoms has a charge of +3. Okay, so this is iron, Roman numeral 3. Sulfur. All right, and the last one, ionic or molecular? It's ionic, yeah. Calcium is a metal, and it has a polyatomic ion in it. Anytime you see one of those, it's definitely ionic. So we write the name of the metal, and we write the name of the nonmetal. This time it just happens to be a polyatomic ion, so this is calcium nitrate. Ringing a bell? Okay. Now, let's let's try this and see what we remember from last week. Or from Friday, I mean. Okay, I would like the formulas for those, please. And in case you can't read my writing, sodium nitride, diphosphorus pentafluoride, cobalt 2 sulfide, and potassium carbonate. Okay. So for our first one, we got sodium nitride, ionic or molecular? It's ionic. Sodium's a metal. All right, so I write the metal. I write its charge, sodium's a +1, okay, and I go with nitride. That's just N, and nitrogen is in group 15, so it's a -3. Okay. Sorry, group 14, -3. Now I got to drop and swap. Okay, so the 1 goes here, but we don't write 1s. The 3 goes here, and we're done. Na3N. I can't reduce that. That's as low as it'll go. Okay, questions on that one? All right, molecular ones are easy because the prefixes just tell us what number to write. Okay, so phosphorus, the symbol for phosphorus is P, di means 2. Okay, fluoride is F, penta means 5, P2F5. All right, and then I've got cobalt 2 sulfide. So cobalt is CO, but has more than one possible charge. Which one do I use? The 2, that's what the Roman numeral is there for. It's to tell me this is the charge you need to use in the drop and swap. And it's with sulfur, which is a -2. So when I drop and swap, I get CO2S2. Am I done?
You need to simplify.
I need to simplify, okay? Now I've simplified, 1 and 1. All right, and then potassium carbonate, ionic or molecular? Ionic, potassium is a metal, right? So we write potassium with a +1, and carbonate, polyatomic ion, CO3. And according to the table, it has a -2 charge. Right? So now I drop and swap, just like with any other ionic compound. The 2 will go here, and the 1 will go here. I don't need to write a 1. Okay. I can leave it like this, or I can do this. Okay. Some people like to always put their polyatomic ions in brackets, and that's totally fine. You don't always need them, like this situation. If the number is a 1, they're unnecessary, but not incorrect if you put them there. Okay, one last one here, just to illustrate something. Ionic or molecular? Molecular. It's got prefixes. They're both non-metals. Okay. N is nitrogen. Di is 2. Bromine is Br. And tetra is 4. Am I done? Some hesitancy on that one. I only reduce what kind of compounds? I only reduce ionic compounds. In a molecular compound, remember, the electrons are shared, not traded. So if the prefixes say the numbers are 2 and 4, the numbers are 2 and 4. Okay, you never reduce a molecular compound. You must reduce ionic compounds because they're always going to be in their lowest terms because they trade their electrons instantly. Okay, just a quick kind of review of differences between molecular and ionic compounds. Okay. All right, so just in case you like having a set of rules to follow at least initially, okay, these are kind of the steps that you can follow for writing chemical names. Okay, so that would be I give you the formula and you need to write the name. Okay, we've reviewed those already, but in case you like having those, okay, the first step is to determine if it's ionic or molecular. Okay, the second step, if it's ionic, write the name of the metal. Okay, then write the name of the nonmetal, ends in "ide." Okay, if polyatomic, write the name as it appears. Okay, metal has more than one charge, use a Roman numeral, right? And then for molecular, write the first nonmetal's name, write the second nonmetal's name, change anything to "ide," put the prefixes in. Okay, I'll give you a minute in case anybody wants to write that down, but those are the steps. Okay, and just a little tip for you guys: if you have the digital workbook and the notes package, the digital copies that you got on Google Classroom are yours to edit. Okay, that's why it has your name on it. So, if ever you need to snap a quick picture of something that's on the board or take a screenshot of it when you're watching it later, okay, you can insert that directly into your Google Doc of the notes package. Some people like to do that and have it as kind of a working document. We used to do a lot more of it when you were allowed your phones in class, but now you're not. But if you need to do that, just ask, and that's totally fine. And you can snap a quick picture and put it in later. Okay. And then for writing the formulas, okay, the instructions are similar. First, you have to determine if it's ionic or molecular. Okay, if you determine that it's ionic, you write the metal symbol in charge, the nonmetal symbol in charge, drop and swap, reduce if necessary, and if there are polyatomic ions, and it's appropriate to do so, put brackets around them. Okay, and then for molecular, write the symbols, and using the prefixes, put in the numbers. Okay, probably a lot easier going from name to formula. All right. All right, so if you have the workbook, okay, you can find this page here. This is what we were just working on Friday, where you have the names and you're going to the formulas. Okay, I'm just going to circle a few here that I would like you to try for right now. You can always go back and try as many as you want. Okay, but let's say number 1, number 3, 5, 8. And 11. Let's say those 5 for right now. Okay, and I'll give you a few minutes and then we'll go over them together. All right, so for our first one, diphosphorus pentaoxide, ionic or molecular? Molecular. It's got prefixes, they're both nonmetals. Okay, so phosphorus is P, di means how many? 2. Okay, and pentaoxide, O, 5. Yeah. All right, and then 16, aluminum phosphate, ionic or molecular? Ionic. Aluminum is a metal. Okay, so we'll have to go aluminum and write its charge, 3+, and it's with phosphate, polyatomic ion, PO4. I believe it's also a -3. Okay, am I right about that? Okay. +3, -3, do they already cancel each other out? If I dropped and swapped, I just have to reduce down to 1 and 1 anyway, so that's my formula. I could put that in brackets if I wanted to. All right, copper 2 nitrate, ionic or molecular? Ionic. Copper's a metal, plus we never have Roman numerals in molecular compounds. All right, so copper with the 2+ charge, and it's with nitrate, which is a polyatomic ion, NO3 with a -1 charge. So I bring the 1 here, we don't write ones. I bring the 2 here, and do what? And close in brackets. CuNO3 bracket 2. All right, how many people are up to number 18? Okay, let's do 18 then. Nitrogen dioxide, ionic or molecular? Molecular. Okay, how many nitrogen?
I mean, one.
1, right. How many oxygen? 2. NO2. All right, and then phosphorus trichloride. Molecular. Phosphorus and chlorine are both nonmetals. How many phosphorus?
1.
Okay, how many chlorine? 2. Oh, sorry, 3. Yes, trichloride, 3. All right, how many people are on 21? Okay. So for 21, potassium carbonate, ionic or molecular? Yep, potassium's a metal, right? So K, and it's a +1. Carbonate's a polyatomic ion whose charge is -2, right? When we drop and swap, the 1 would go here, done with that. The 2 would go here, done with that. If I want to, I could enclose that in brackets. All right, and the last one, lead 4 chloride. Ionic, okay? Lead is Pb. The Roman numeral tells me that's the 4+ charge. It's with chlorine, which is a -1. Drop and swap. Yeah, PbCl4. Okay, how are we feeling about those? Okay, that was a mix of some that were, fairly easy and some that were pretty tricky. Okay, I would like you to give me the names of the ones that I circle here. Okay, let's try those 6 there. Okay, so for question number 4 there, we got calcium and we've got sulfate, so ionic or molecular?
Ionic.
It's ionic. Calcium is a metal. Okay, this stuff is simply calcium sulfate. Okay, we just follow the ionic rules, which is write the metal and then write the polyatomic ion. All right, number 5, we've got another ionic compound, aluminum with bromine. Okay, and so this is going to be aluminum bromide. No prefixes because it's ionic. Okay, number 8, ionic or molecular? Molecular. Okay, and you should probably know this stuff right off the top of your head. CO2 is carbon dioxide. Yeah. Okay, and number 9, ionic or molecular?
Ionic.
Ionic. Hydrogen's listed first. It behaves as a metal. This is hydrogen nitrate. Okay, and then number 11, all right, we've got ammonium listed first again, so that's an ionic compound. Ammonium chloride. Okay, and then number 12, ionic or molecular? It's molecular. This is sulfur tetra. Okay, we may or may not get some time here throughout the week to work on that with our first lab, but we'll try to throw a few more minutes here and there of practice in on that. For your quiz this Friday, the best practice quizzes to do are 1, 2, and 3. Okay, just a quick reminder of where you find those. Whoop, wrong one. Okay, you find those in the classwork tab. What the heck is going on here? Okay, you find those in the classwork tab. Practice quizzes and solutions. You're looking at chemistry. Okay, and if you scroll in there, all of the quizzes are there, and then if you scroll down, there's a link here that takes you to YouTube where the videos of the solutions are. So it's me doing the solutions so you can see if you did them right. Okay, any ones you don't get right, you should probably come in and ask about. Okay. All right, let's have a look at lab report expectations here. All right, so that's the handout that I just gave you. Come on. There we go. How many of you have actually written up a full lab report before? Okay, I usually don't get too many hands on that. So this is going to be your first real lab report that you've ever written up, but you've probably heard all the terms that I'm going to use. They're all part of the scientific method, okay, so nothing really new there. Every lab is going to start out with a problem. That's the thing you're investigating. Okay, for our lab this week, the problem we're going to be investigating is how unknown substances can be identified with their physical properties. All right, so what you're going to have later on this week is a whole bunch of unknown compounds, okay, and their beakers are just going to be labeled with A through K, and you're going to have to use just their physical properties, okay, color, solubility, pH, all that kind of stuff, to identify them from a list. You don't just have to pull them out of a hat. There'll be a list, and you'll just have to match it up. Okay, so that's what we're going to be doing. We're just going to use a very simple experiment on plants, okay, as our example here. All right, so a typical problem could be something like, what is the effect of light on plant growth? I mean, that's pretty obvious, but let's just use it as an example. All right, the design portion of your lab report is worth 5 marks. Every lab report is out of 30, by the way. Okay, so this is 5 marks out of the 30. In the design is where you tell me what your manipulated variable, responding variable, and controlled variables, plural, are. Okay, so just as a quick review, the manipulated variable is the thing the experimenter is changing in order to see what its effect would be. The responding variable is the thing the experimenter is watching, measuring. It could be more than one thing, but watching and measuring to see. That's how it's going to measure the effect. This is the thing that's going to change if the experimenter is right about their idea. Okay? And then the controlled variables are the things that have to be kept the same, right? Because they could also affect the experiment, and we don't want them to, because we only want to see what the manipulated variable does, so we control all the other stuff. Okay? The expectation for you in a lab report is 2 things. For each of the variables, you identify them. So you tell me the manipulated variable is this. And then you explain to me why or how it's being manipulated. All right? So as an example, for our experiment on the effect of light on plant growth, the thing the experimenter would change would be the amount of light each plant receives. All right? So they would probably need, a half a dozen plants, and each one of those plants would get a different amount of light. Okay, so maybe put them all in boxes with a little light at the top, and he just has a timer that turns one of them on for 6 hours a day, or one of them for 12 hours, one for 18, one for 24, and one sorry plant that gets no light at all. Okay, because you got to have a control, right? If we got to know that if a plant doesn't get any light, it's going to die. All right, we have to have that proof. All right, so we would say in our experiment then, okay, the amount of light given to the plants is the manipulated variable because all subjects will receive different amounts of light, and light powers photosynthesis. So I've identified that light's the manipulated variable, and I've explained how and why it's being manipulated. The how would be they're all getting different amounts. Why? Because light powers photosynthesis. Okay, everybody kind of follow me there? It's going to be, a sentence or 2 for sure. Okay, you don't just say light. Right? That's not going to get you 4 marks. You got to have an explanation. Your responding variable, as we said before, is whatever changes as a result of what you did. It's the thing you're going to be watching and measuring and whatever. Okay, so very simply here, the responding variable will be the growth of the plants. That's the thing that's being observed, okay? Because the plants getting more light have more energy for growth. I would also say that as part of this, you should probably say how you're measuring this. All right, so for the responding variable, okay, it could be like measured by height of plants. Okay, that would be a quantitative observation because you'd actually physically measure the plants every day. You could also have a qualitative observation where you take pictures of the plants every day and then you have those to look at and see, well, this plant is like yellowed and stunted and this plant is green and healthy and that plant is crusty and dead. Okay, like you could have those observations in addition to this plant got really tall and that one didn't grow because it died. Okay, sort of making sense? So you tell me there, here's the responding variable, it's the growth of the plants, here's why it's responding, here's how it's being measured. All right, if you didn't add that, you should add that to your sheet right now, okay? Have it in there that there's, part of your explanation should be what you're measuring or how you're observing, okay? We're gonna have one lab in here where you're gonna take pictures of the plant before and after, and you're gonna measure how much water it uses, okay? So you're actually gonna have two forms of observation. Okay, your controlled variables are all the things you keep the same because they could also affect your experiment. So for a plant, if I only want to see what the effect of light is, I need to control all the other things that are helpful for a plant to live. All right, that means every plant should get the same amount of water. They should get the same amount or the same temperature. They should grow in the same quality and amount of soil. Okay? Anything that could affect the growth of a plant could throw off my experiment. So I have to make sure that all of these other things are the same for all of my plants. For the lab we're going to do on Thursday, things we would probably want to keep the same would be like we use the same amount of everything, because otherwise it's not a fair comparison. If I got a giant pile of sample A and 2 grains of sample B, it's hardly a fair comparison. Okay, so controlled variables are the things that could affect my responding variable if I don't keep them the same. Okay, everybody kind of follow me there? Okay, in a lab report, you would be expected to list and describe 3. There's going to be more than 3 controlled variables in any experiment. You are only required to determine and describe 3. How many manipulated variables can there be? You can only have 1 manipulated variable. If you try to test more than one thing at a time, will you ever know which one had the greater effect? So you can only ever have 1 manipulated variable. Okay, and then responding variables, you could have more than 1 of those. Most of the time we only have 1, but there's the odd time where you might be watching more than one thing as an indicator of something. Like in this example here, we said we take pictures of the plants and measure their height. So then we've got kind of 2 things that we're using to help us determine the growth of a plant. Okay, so for this one here, okay, things that we would keep the same species of plant. Okay, different plants grow at different rates. It would hardly be fair if I had like a bean and a giant sequoia in this experiment. They're completely different plants. I'd probably just plant all beans from the same bag, and then I'd know that they're all the same. Okay, same amount of water, because water is an important factor in plant growth. So each plant needs the same amount, so it can't affect the growth of the plant. So there's identification, and here's how and why it's being controlled. In other words, it would affect the experiment this way if I didn't control it. Okay, that's going to be part of your explanation. Same soil, because plants get nutrients from soil, and different soils hold water differently. Keeping them the same ensures that it cannot affect the experiment. Okay, same temperature. As plants typically slow their growth in extreme heat or cold, choosing an effective temperature for all plants ensures it does not affect the experiment. Again, I identified how, I'm keeping them all at the same temperature, and why it affects the growth of a plant. Okay, that's what I would expect to see in your lab reports as well. Tomorrow I'm gonna hold your hand through the first lab report, the pre-lab stuff, so you kind of get an idea of what it's like. Okay. All right, questions so far? So that's the first 5 marks out of 30, is just identifying and explaining the variables. One manipulated, responding variables, usually just one, maybe there's 2, always 3 controlled variables. All right, once you've done that, then the next part is your hypothesis. All right, now, if you've ever written one of these before, you were probably told it's an educated guess. We don't guess. Science is not about guessing, okay? Science is about inferring something, okay? So a hypothesis is not a guess, it's a statement. And that statement has to be set up so that it can be proven right or wrong. Okay? And it's okay if at the end of a lab you have to reject your hypothesis. If your hypothesis ends up being wrong and you say that in your conclusion, that's okay. Right? You're not going to lose marks because you said something that ended up being proven wrong by the experiment. That's actually how most science goes. Most of the time people are not right on their hypothesis. It gets proven wrong by the experiment and they try something different. Okay? So a hypothesis is always going to have 3 words in it. It's going to be more than 3 words, but it's always going to have these 3 words in it. If, and, then. Okay? And it goes like this. If this is true, and an experiment as follows is performed, then the results will be as follows. Okay? That way, you're going to be right or wrong. You're either going to get those results or not. Okay? And at the end, you'll go, the hypothesis is acceptable because as predicted, the plants did this. Okay? But in your hypothesis, you would need to say something like this. All right? If plants require light for growth, and 5 identical plants are given different amounts of light, then the plants that receive the most light will show the most growth. Okay? Pretty simple hypothesis. It says that I think light affects plant growth positively. Okay? It says what I'm going to do, 5 different plants, they all get different amounts of light, and it also says at the end, then the plants that get the most light will grow the most. Okay? Everybody follow there? That's a pretty simple hypothesis, but that's the general blueprint for a good hypothesis. If this is what's going on, or if this is what's causing something to happen, and an experiment like this is run, then the results will be as follows. Okay? Notice that I never put the word I, us, we, or you in the hypothesis. Is it important to not use like first person stuff? It is, okay? You have to distance yourself from it. Otherwise, anytime someone else tries to replicate it, you have to be involved if you are in the hypothesis, okay? So a hypothesis should never go, I think this will happen. This is gonna sound really awful, but I don't care what you think. I care what you can prove, okay? And this is a hypothesis that can be proven or disproven, okay? What you think can't. You either think that or you don't, but you need proof one way or the other. Okay, everyone kind of follow the idea there? Okay, so it's an if, and then statement that communicates what the relationship between the manipulated and responding variable is thought to be. That's the if part, if light affects growth. Okay, briefly describes the experiment, that's the and part, and 5 different plants are given different amounts of light. Okay, then it outlines the expected results. Then the plants that receive the most light will show the most growth. Okay, everybody all right with that? All right. After that come your materials and your procedure. Those are always going to be given to you. All right, so there will be a list of materials, okay? It'll just be there, you don't have to fill it in, it's already ready. And there'll be a procedure for you to follow, a numbered list. Okay, you follow it step by step. It's pretty cookbook most of the time. All right. Questions there? By the way, when you do a lab report, you always get a template. All right, so I will give you a Google Doc and it'll have like all of this stuff. It'll say hypothesis and then there'll be room for you to type afterwards. So the skeleton will always be there for you. All right, so as we said, if, what's the cause of the problem or the relationship, and briefly describe the experiment, then what to expect if you are right. Okay, we generally avoid I, us, or we in a hypothesis. All right, as we said, procedure is your detailed step-by-step explicit directions right? Your observations, you record those. Usually I'll give you like a chart that you can fill in, or maybe you're going to insert pictures that you take, or just write in observations that you make, okay? Once we have those, then we go to the analysis. The analysis is usually going to be questions or calculations. They're going to be there already. You just have to do them and put them into the lab report. If you want to do them on paper and take a picture of that and insert the picture, I'm also fine with that. I just don't take anything on paper. Okay? It all has to be done in the Google Doc. All right, so you'll answer those. Make sure your answers are thorough and detailed and all of that good stuff. For the conclusion, first thing you do is you copy and paste your hypothesis. So just go right back up to the hypothesis, highlight, copy, paste it down here. All right, that way I can refer back to it without having to scroll up to the top of your report. Then you're going to tell me, can you accept or reject your hypothesis and why? All right, so it's going to be a few lines for sure because there's some explanation in there. So let's say that my observations for this lab were that the plant that got 0 hours of light died. The plant that got 6 hours of light grew very little. The plant that got 12 hours did pretty well, grew quite a bit. The plant that got 16 hours grew a lot. And the plant that got 24 hours of sunlight died. Is my hypothesis acceptable or not? My hypothesis said the plants that receive the most light will show the most growth. Did that happen? It didn't. All right, so in my conclusion, I would have that hypothesis there, and then I would say, as it was found that plants receiving small amounts of light and very large amounts of light showed very little growth / died, okay, it can be concluded that plants require a certain amount of light and dark to be healthy. Therefore, the hypothesis is rejected. Okay? I've said what my data says, I've explained it, but I've also said it does not support my hypothesis. And that's okay. All right? Everybody okay with that? The only way you lose marks in here is if you accept a hypothesis that shouldn't be, or you reject a hypothesis that should be. Okay? All right, and then the last part here is the evaluation. You need to identify 2 sources of error and give me ways to fix them. All right? They can't be human error. All right? I oftentimes have people like, we accidentally spilled some of substance E into substance B and that affected our results. And then you should have done it over again. You know you made that mistake and you just kept going? That's not something you want to tell me. Okay, because now I'm going to go back over your lab report and go, okay, didn't do that, and it's going to be bad. Okay, if there's a human error, you fix it during the lab. It should never be reported at the end because it should never affect the experiment. What we want to list here are things we could improve about the design that could make it better. So, we might say that it was difficult to control the temperature inside the individual boxes because the lights actually gave off some heat. And so the plants that had the light on for longer also had slightly warmer temperatures than the other plants. This could have affected the results. In the future, there should be climate control in each one of the boxes. Okay? That's something that you didn't foresee when you designed the experiment. You said, here's how it may have affected the experiment, and here's how I make it better in the future. Okay? You have to find 2 of those. Guys, they're always built in. Okay? You're not going to hurt my feelings by finding the mistakes or the things that could be done better. There's always going to be some in there for you to find for exactly this purpose. Okay? Sometimes people get shy about being critical. Be critical. Okay? Science is about being critical. All right, so the evaluation's out of 3 marks, the conclusion's out of 4, okay? The observations that you make are out of 3, the analysis is out of 5, okay? And the hypothesis is out of 5. Okay? So it all adds up to 30 at the end. All right, tomorrow we are going to go over properties of compounds and we are going to do the pre-lab for Thursday. Thursday, we're going to do the lab. Friday, you got a quiz. That quiz will be on structure of the atom and naming. Okay? There won't be any of the properties of compound stuff that we go over tomorrow. Okay? It will all be naming and structure of the atom. All right, good work today, guys.